this. Okay, and maybe F5.
Can you go to full screen mode, please?
I'll try. Wait, I'll get my son to help me. He'll know how to go to sleep.
Okay.
Yeah,
okay.
How did you do it?
Okay, great.
Okay, I'll just go back and this one. Okay. This one. Great. Okay, excellent. Now let me put my video on. I think my video is off, so I'll stop share, put the video on, and come back.
Sure. Okay. Okay. Great. Okay.
Right.
Good. Good. We are all set. Okay. There are still a few minutes, but
Sure.
if you're ready and this audience are there, we can start whenever you want.
It's really up to you, Shaheen. You should say.
Okay. So we may start because everything seems to be ready. And
okay.
Let me just, it's a great pleasure to have S.Minwalla, and he's going to tell us about the Hilbert space of Chern-Simons matter theories. Please, Shiraz.
Okay, it's very nice to be back at this conference. Last year, it was one of the first virtual conferences I spoke at, so it was a bit of a pioneer, and it's great to see this conference continuing. Okay, so my talk is titled The Hilbert Space of Chern-Simons Matter Theories, and is a follow-up on the talk I gave a year ago at the same conference, reporting more progress on the subject. So let me keep going. This talk is based on a paper to appear, hopefully in the next month or so, written together with Sachin Jain, Amyo Mishra, Naveen Prabhakar, and Tarun Sharma. Amyo is my PhD student. Naveen is a postdoc from TIFR who just moved on to ICTS in Bangalore. Tarun is my ex-student who's now a faculty at the Indian Institute of Technology, Delhi. Though almost everything I say will be based on work on this from this upcoming paper, the basis for this talk will be a number of earlier computations and results, which are listed here. And I'm not going to give detailed references again as through the talk. So let me start. Okay. Consider, so the topic for my talk today is going to be the study of Chern-Simons theories in 2+1 dimensions, coupled to dynamical matter fields. So let me start this talk by motivating the study. Chern-Simons theories coupled to dynamical matter fields are of interest for several reasons. First, in parity non-invariant theories, in 3 dimensions, the one-dimensional Chern-Simons Lagrangian generically dominates, is more relevant than, and so dominates over the 2 derivative Yang-Mills action at low energies. Consequently, if you've got a parity non-invariant theory in 3 dimensions with a gauge field, and you go to very low energies, either the theory will be gapped. Generically, the theory will be governed by a Chern-Simons type theory in the IR. Now, the theory might be either gapped, or if you're lucky, if you're fine-tuned, will be Chern-Simons matter theory. So Chern-Simons theories, and sometimes with matter, describe the generic low-energy behavior of parity non-invariant gauge theories in 2 dimensions. Also, some parity invariant theories. So that's one reason to be interested in them, the generic IR behavior of 3D gauge theories without parity. Second, the Chern-Simons coupling, the analog of the Yang-Mills coupling in Yang-Mills theories is the inverse of an integer. Because it's the inverse of an integer, it's a discrete quantity, and so cannot flow continuously under the renormalization group. Okay? Because of that, beta functions for the Chern-Simons kinetic term are always automatically zero. This tells, just this fact immediately implies that it's very often very easy to generate conformal dynamics in Chern-Simons theories. You take a Chern-Simons matter theory and you fine-tune the mass away. The dynamics of the theory is very often very easily automatically conformally apparent. So that's another reason to be interested in these theories. They give you an easy way of generating many infinite classes of new interesting interacting conformal field theories without supersymmetry. Third, Chern-Simons matter theories host anionic excitations, and generically with non-half integer spins. Okay. These anionic excitations are different. They're different from bosons, the bosons or fermions that we are more usually used to. And this difference shows up in many ways. As I said, for instance, the spins of these excitations are not always integer or half integer. But more generally, there's interesting dynamics associated with this difference. One interesting bit of dynamics that's only been partially understood so far is that the S matrices of these anionic excitations do not obey the usual rules of crossing symmetry, at least naively. Okay, so these theories have novel, interesting new dynamics associated with the fact that the particles that they describe are anions. Fourth reason to be interested in these theories is that some of these theories have conjectured ADS-CFT dual descriptions in the large angular limit. I mean, the prototypical example is, of course, the AB-JM theory, which is a Chern-Simons matter theory. More funny examples are Chern-Simons matter theories with fundamental matter, which have conjectured ADS-CFT type dual descriptions involving not gravity, but Vasiliev theory, which is also interesting in its own way. Fifth, some of these theories enjoy conjectured strong weak coupling Bose-Fermi dualities. Okay, so field theory dualities. On one side, a theory with Chern-Simons coupled to bosons, and the other side of the theory with Chern-Simons coupled to fermions. And these theories enjoy these conjectured strong weak coupling Bose-Fermi dualities, even in theories without supersymmetry. That's sort of interesting. Now, finally, and for the purposes of this talk, most importantly, these theories are actually theories you can meaningfully study. Okay, and though this is an oversimplification, the two things make these theories particularly easy to study. These two things are that there are two interesting limits of these theories, both of which are exactly solvable in their own way and yield a lot of information. The first limit is an old one. Suppose you take a Chern-Simons matter theory and you take the matter mass to infinity. Then what you're left with is pure Chern-Simons theory. And pure Chern-Simons theory, as we all know, was exactly solved by Witten in about 30 years ago. The solution is beautiful, intricate, and carries a lot of very interesting both physics and mathematics. So that's one exactly solvable limit of these Chern-Simons matter theories. The second exactly solvable limit of these Chern-Simons matter theories is a more recent one. It's a limit in which all the matter fields are taken to be only in the fundamental representation. And the number of flavors, the number of the rank of the gauge group, N, and K are both taken simultaneously to infinity in a coordinated matter so that N divided by K, more precisely N divided by N plus sine K times N, this quantity that we call lambda, is held fixed. In this limit, the theory is once again more or less exactly solvable. Many quantities in this limit have been computed precisely, exactly as to all orders as function of this lambda. Now, this lambda is sort of the analog of the Toft coupling in more familiar planar gauge theories. It's the quantity that tells you how big a two-loop graph is compared to a one-loop graph. Okay, So the fact that you can solve this theory to all orders in lambda tells you that this theory is exactly solvable even where it's strongly coupled. And this holds out the promise of studying some of these interesting strongly coupling dualities and other phenomena in exact results. Because the only way you can study strongly coupling duality in exact results is if you get exact with computations, if your computations work for all coupling, not just for weak coupling. Okay, great. Now, so these matter-Chern-Simons theories are interesting. I hope you agree that they're interesting for the reasons I've reviewed behind and perhaps for others. Now, as I said, the focus of my talk is going to be the solvability of these theories. Now, solvable limits of theories are usually special. In particular, if you've got a solvable theory, it often happens that the Hilbert space of that theory has a nice, intricate, but understandable, nice structure that you can understand. Sometimes this Hilbert space is obtained by taking some free structure and imposing a non-trivial constraint on it. And that gives you a non-free, but sort of easy to understand structure for this Hilbert space. In this talk, I'm going to ask, I'm going to present such a description for the Hilbert space of matter-Chern-Simons, these fundamental matter-Chern-Simons theories in the large N limit. Okay, I'm going to ask what kind of Hilbert space these theories have, what we can say about them, what interesting physics the answer contains. Now, the starting point for my analysis will be earlier results that have been obtained over the last 8 or 9 years through various computations by various people, including my own group. The starting point for my talk, and I'm just going to review the answers of the starting point. I'm not going to explain how they were obtained. The starting point for my talk will be the all orders expressions for the thermal free energy of these large N Chern-Simons matter theories on S2 tensor. Okay. These have been computed in these papers, which were referred to at the beginning, by analytically summing all planar diagrams using various tricks. How they've obtained, for this talk, forget, we won't worry about that. Okay, I'm going to use the final results, in fact, in the most complete of these final results, as the starting point for this talk. So we know the free energy as a function of temperature, and I'm going to ask the inverse question. What Hilbert space do these theories have so as to give rise to this free energy as a function of temperature? Okay, so in order to be able to ask this question, I will first start my talk by presenting the detailed results for the known answers, which I will do over the next slides. But if there are any questions or comments, first about the motivation and what I'm going to try to do, this is a good time.
So, Shiraz, it's not about this last slide. I was wondering how much of the things that you reviewed and the motivations would also be there for non-compact gauge groups. For non-compact gauge groups, do we have this as some of the results that you reviewed?
Hi, Shaheen. Sorry, I lost my just a minute. Could you please repeat the question? I'll get my talk back up.
Okay. So it was a question about what you reviewed about the results from the literature. Yes. And the question is, what about the non-compact gauge groups? So I know that you are only interested in the compact ones, but can you make some general comments?
So non-compact gauge groups. Okay, interesting question. I have thought so little about these that no, I won't try to make any sorry, I won't try to make any comments here because I'll probably end up saying something wrong. Right, the one, the one comment is that non-compact gauge groups, if you want to make them, no, so I just won't try to make it. Sorry, Shaheen, I won't say anything sensible.
Okay, I know it's not related directly to your work, but I was just curious.
Yes. No, it's an interesting question, and I should have some. Yeah, I'll think about it and get back to you if I have anything.
Okay, so would you please also share your slides again?
Oh, I'm not doing that. Yes, sorry. Can you?
Yes, but again, the full screen mode, please.
Yes. Just a minute. Sorry. And now. Okay.
Oh, yes. Okay, please.
Okay, wonderful. Okay. Sorry. Okay, great. So, so the way I'm going to start the rest of this talk is to review the results that are known for these thermal partition functions, okay, in these theories, and then I will try to interpret. So the next few slides will just be a review of known results. The results themselves are a bit complicated to state, but we'll learn to see beauty in them. So please hold on for the next few minutes. Okay, so in the limit n goes to infinity, k goes to infinity, and the volume of the space that we're working on goes to infinity. With all ratios of these quantities, so n by k is held fixed. Also, the volume is taken to infinity, scaling like n. Okay, but the temperature, chemical potential, and all masses and couplings held fixed. So in this sort of strange coordinated limit, n goes to infinity, k goes to infinity, soft limit, but also volume goes to infinity, scaling like n. So you should think of this as almost like being on R2. Okay, the partition function of the theory on S2 times S1 has been shown to be given by an expression of the following structure. The partition function on S2 times S1 is given by an integral over a holonomy, okay, of an expression that depends on the eigenvalues of this holonomy field. So this U here is a single unitary matrix, which should be thought of as the zero mode of the holonomy around the time circle on the S2 on the 2 sphere. Okay, so the partition function on S2 times S1, it takes the form that it's given by an integral over a unitary matrix, and then there's an action which depends on the gauge invariant part of this unitary matrix. Now we're working the large n limit, so the most useful way to capture the gauge invariant, so all the gauge invariant information about the holonomy matrix is in its eigenvalues, and in the large n matrix, it's a good way to keep track of this information is to keep track of the density of eigenvalues. Okay, so the density of eigenvalues defined in this equation 2 here, rho of alpha, which is 1 over n delta of alpha minus alpha j, where alpha j is the various eigenvalues of the holonomy. This, in the large n limit, usually forms a continuous function. Okay, this integral here is the usual Haar measure over all the eigenvalues, with one constraint. The constraint turns out to be that we only integrate over those unitary matrices such that the density of eigenvalues of these unitary matrices in magnitude is less than equal to 1 over 2 pi modulus of lambda. Okay, so this comes out of some interesting calculations. Now, I have to tell you more about what this V of lambda is, this V of rho is. So I'll tell you about that. So this V of rho in this function depends on the details of the matter-Chern-Simons theory under study. In this talk, I'm going to study two such theories. The first one I call the fermionic, regular fermion Chern-Simons theory. The second one I call the critical boson Chern-Simons theory. Okay, so regular fermion theory is, for instance, an SUN theory, Chern-Simons coupled SUN theory, coupled to a fermion that's massive but would otherwise have been free in the absence of the Chern-Simons coupling. The critical boson theory is a theory of bosons that would, in the absence of the Chern-Simons theory, have been a Wilson-Fisher boson theory with the mass deformation when coupled to the Chern-Simons theory. Okay? And when I talk about the fermionic theory, I will use the symbol NF for the rank of the gauge group and KF for the level of the gauge group. When I talk of the bosonic theory, I will use the symbol NB for the rank of the gauge group and KB for the level of the gauge group. Okay. Now, here I've given examples where one side is the fermions is SUN, the bosonic side is UN. We will need to deal with both SUN and UN theories. I will give you more detail of that subtlety as we go along. Okay. So, but for instance, suppose we were doing the SUN fermionic theory and the UN bosonic theory. In the large and limit, it's very little difference in the explicit formulas. Okay. For each of these theories, explicit computation gives us what precisely this V rho function is. And I'm now going to present these functions. For each of these theories, we find that this V rho takes a particular form. Remember, rho is the eigenvalue density function. For each of these theories, V rho takes the form that V rho is the minimum, is the extremum, the minimum over a set of auxiliary variables of a function that we call the off-shell free energy, which is a function not just of physical quantities like the temperature and the chemical potential and the couplings of the theory as well as rho, but also of some auxiliary quantities which we call zeta. And this quantity is what comes out of the calculation. And then after you get this quantity, you're supposed to extremize this quantity or minimize this quantity over these auxiliary quantities zeta. Okay, so now all that was very abstract. Let me tell you more precisely. In the case of the regular fermion theory, zetas are two things. There's this thing we call CF hat and the thing we call C tilde. Okay, and this turns out to be the result for the off-shell free energy, the function of the free energy that's a function of this rho of microscopic parameters like the fermionic mass, but also of these auxiliary quantities. Remember, at the end, what we're supposed to do is to take the answer from this theory and extremize them over these auxiliary quantities, CF hat and C tilde. Okay, and here in this I've used symbols like mu hat. Mu hat is the chemical potential of the theory divided by the temperature, and MF hat is the mass of the UV mass divided by the temperature. Now, this free energy has a first line, a second line, and a third line. Only quantities in the third line here depend on the eigenvalue density and on the chemical potential of our theory. The first two lines don't depend on either. So this third line will be special, as we will see. Okay. But before we come to that, now let's go on to the case of the critical boson theory. Once again, this critical boson theory, this object, this functional of rho that we have to integrate over is given by an auxiliary, an off-shell free energy that's a function of auxiliary variables. In this case, these auxiliary variables are called CB and S tilde. Okay, and we get this particular expression. Note it's very precise, right? There are 3x2s and 4s and 6s, and there's no ambiguity. In this quantity, there's this first line, second line, and third line. Only quantities in the second and third line depend on rho, the eigenvalue density, and on chemical potentials. Note that the expression here, this third line here, and this second line here are very similar. But the boson has this one extra term that looks really fun. There's a theta function. It looks to start with non-analytic, though it gives rise to an analytic free energy. There's a theta function that kicks in only when the chemical potential is larger than the thermal mass, the CB though I didn't tell you that, I've said it here in the slides, has a physical interpretation. The interpretation is that of the thermal mass of our subject, of our theory. Okay, the mass of our bosons, thermal mass of the bosons at this temperature T. And so this term is 0 unless the chemical potential is larger than the thermal mass. And when it's larger than the thermal mass, you get this extra term. It's a strange term coming only when the chemical potential is above the temperature, above the thermal mass. It's part of the universal part of the answer because it depends on the chemical potential. Okay, so once again, only the last two lines of this expression depend on either rho or on mu. Okay, so let me summarize. If I take the partition function of my theory on S2 times S1, both for bosons and fermions, I get this integral over holonomies with a Chern-Simons modified Haar measure. It's the usual Haar measure, except there's an exclusion. You're not allowed to integrate over those unitary matrices whose eigenvalue density functions exceed a certain bound, 1 over 2 pi lambda. Okay. Now, and then the thing that we integrate over is the extremization or minimization over some auxiliary variables of an off-shell free energy that depends on these auxiliary variables and on the eigenvalue density function for this holonomy matrix. Now, in general, I mean, if we were just working at finite n, there's nothing more we could say. However, notice that when we're working at large n, and this we've already alluded to in a way, the integral over these unitary matrices can be performed in the saddle point approximation. So the integral over these unitary matrices can be performed by performing an extremization. But remember, we are also extremizing over these zeta variables here. So this full answer can be obtained by a double extremization. Now, if you're performing two extremizations, you can perform them in any order. You get the same answer. So we can interchange these two extremization procedures. So we're allowed to take the minimization of zeta I outside and then do the integral over du. This is allowed in the large element. Okay. And so the evaluation of this S2 times S1 partition function can be performed in two steps. In step 1, we evaluate the integral over the holonomy matrices of this off-shell free energy at fixed constant values of these auxiliary parameters zeta I. We do it only for constant values because we know beforehand that the extremization will only occur at constant values. Okay, and then in step 2 we extremize the result of this, the first step, over all zeta I. Okay, almost everything interesting in my talk will be in step 1. We'll come to step 2 right at the end of this talk. Okay, so explicit calculation, just to recap, tells us that the partition function is given by 2 steps. Extremization over a few finite number of constants, the zeta i's, of something. This of something is this quantity. Now, recall that in order to perform this integral over u, we only need to keep in the bosonic part the terms in the partition, the terms in the off-shell free energy that depend on u, that depend on the eigenvalue density function. Okay, because that's where the information over u is. The rest is constants as far as the integral over u is concerned. Now, sorry, this was the bosons. Sorry, but for the fermions, the only part of the off-shell free energy that depends on this eigenvalue density function is this third line. Okay, and therefore, in step 1, all we need to do is to evaluate this relatively simple quantity. We need to evaluate the integral over u of this relatively simple expression. Now, this expression is not just simple, it has an interesting Hilbert space interpretation. It's very easy to convince yourself that this quantity here is simply the trace over the matter Fock space of e to the power minus beta h minus mu q of the simple free Hamiltonian of free matter Fock space and free charge of free matter Fock space, twisted by the holonomy matrix U, where the free Fock space is a free Fock space of fermions with mass CF. Okay, and propagating on a large S2. So this quantity, the quantity over which we have to do the integral over U in order to obtain IF, has a very simple interpretation. It's the trace over a free Fock space twisted by the holonomy U. Okay, and then we have to do the integral over U. So IF, the end product of step one, is simply the integral over the holonomy of this trace over a very simple Hilbert space, where the Hilbert space is that of a free Fock space of fermions of mass CF. The CF, remember, was one of the auxiliary parameters of the problem and will be extremized in step two. But for step one, we forget about it. It's just some mass. Okay, that's great. How does it go for the bosons? For the bosons, we are instructed to evaluate a similar kind of thing. We're instructed to evaluate this integral over U over a bosonic partition function, where once again, line 2 of the bosonic partition function was simply the trace over the Hilbert space, over the Fock space of free bosons of mass CB, with the usual kind of Boltzmann factor twisted by U. But now for the bosons, remember, there was this one extra term, which also depended on the chemical potential, so we want to keep that here. And this one extra term is this funny theta function piece. So I keep that as well. So what we're supposed to do for the bosons is to evaluate this trace over the free Hilbert space of this quantity times this other stuff, and then do the integral of that over U. This gives the full mu dependence of the partition function, and then later we're going to extremize this over in step 2 over the zetas. Okay. Now this looks very, very familiar. The structure looks very, very familiar. And I'm going to remind you in what sense it looks familiar. This, remember, this integral over Haar measure was a funny integral over Haar measure. It was a Chern-Simons modified integral over Haar measure because it would have bound in the eigenvalue density densities of eigenvalue density functions. Suppose for a moment we allowed ourselves to replace this funny integral, okay, this funny measure, by the ordinary Haar measure. Then we would have got that for the fermions we need to calculate this quantity where du is the usual Haar measure. Okay, and we could ask what is the Hilbert space interpretation of this? Now the Hilbert space interpretation of this is very familiar. It's very simple and very familiar. You see, what we're doing is we're taking this set of free fermions that have invariance under a UN global sort of symmetry, which is actually gauged, but before you do the integral over U, acts like a global symmetry. And by doing the integral, by putting this U here and doing the integral over U, what we're doing is projecting to the UN invariant or SUN invariant part of that Hilbert space. So I tilde F, had we replaced this Chern-Simons modified Haar measure by the usual Haar measure, I tilde F would just have been the projection onto the UN or SUN, depending on which gauge group we were dealing with, of the UN or SUN singlet sector of the free Fock space. Okay, that's what I've written in this formula. Question. That is what happened when we ignored a subtlety. This U was, this is what comes out when we use the actual Haar, the true Haar measure, not this Chern-Simons modified Haar measure for this problem. Question, does IF have a similar interpretation to I tilde F? Okay, and next question, what about IB? IB doesn't have such a simple interpretation. Even I tilde B doesn't have such a simple interpretation because of all this other stuff here. So first question we're going to ask is, does IF have a nice simple interpretation? And then what's the deal with IB? Okay. So I'm going to claim that the questions asked at the end of the last transparency have a very simple universal answer, both for the case of fermions and for the case of bosons. But in order to explain that answer to you, I'm going to have to go into some technicalities about Chern-Simons theories. Okay, so and the claim is that the answer is this, that in both cases, what we get when we integrate over this Chern-Simons modified measure for U is we take the Fock space and project it onto the space of Wess-Zumino-Witten singlets, rather than group theory, Lie algebra group theory singlets. That's the claim. Now, in order to explain what this word means, what these words mean, and why it's true, I'm going to have to go into some technicalities. So this is a good time to pause to ask you if there are any questions or comments. Any questions or comments about the motivation, about what I've said, whether it makes sense?
So, hi, Shiraj.
Hi, is this Takeshi?
No, Shumit.
Oh, hi, Shumit.
Hi. So just for clarification, this object I tilde F is just the usual fermionic theory, no Chern-Simons term, and by hand I impose a condition of UN singlets.
That's right. That's if you were to just take fermions that were UN invariant and just by hand, as you say, impose UN singlet condition, that's what you would get. Of course, this I tilde F never actually appears in our computation. It was
right. I understand. Yeah. Yes.
Okay. This is what would appear if you took just a Yang-Mills kind of theory and take the gauge coupling to zero limit. Of course, there you would get also gauge bosons apart from the matter, because in that limit the only interaction left would be the overall Gauss law singlet condition.
Right. Okay.
Fine. So I'm claiming that the actual answer has an interesting twist over this projection onto Gauss law singlets. We get the projection onto SUN singlets, Wess-Zumino-Witten singlets. And now I'm going to try to explain this to you. Any other questions? Great. Let me go. So I have to explain what I mean by Wess-Zumino-Witten singlets and why that's relevant. So first, SUNK Chern-Simons theories and their Wess-Zumino-Witten duals are relatively familiar to most of us. As most of us know, they are characterized by single level K. Now, I'm going to have to deal with slightly less familiar Chern-Simons theories and their Wess-Zumino-Witten duals. These are UNKK prime Chern-Simons theories. Now, these theories may be less familiar to you. To start with, they're not characterized by one level, but by two. The reason for this is that UN theory at the level of algebra is SUN times U1. And so roughly speaking, what you have is one level for the SUN part and one level for the U1 part. Now, of course, globally, UN is not exactly SUN times U1. Right? There's this, you have to mod out by a Zn that acts on the U1 and the center symmetry of the SUN. So these two things are linked together. And that linking, when you go through what its consequences are, tell you that this K prime here cannot be absolutely any integer, but has to be the shifted level of the SUN theory plus an integer times n. Okay, so the level of the SUN theory, roughly speaking, plus an integer times n. Okay, so now there's still a two-parameter set of theories. You can choose the level of the SUN theory as you want, and then you can choose this Q as you want. So there's still a two-parameter set of theories. We are going to be interested particularly in two values of this Q. The first value of this Q is Q equals 0. In this case, the kappa here, by the way, is the shifted level. Okay, K plus sine K times n. You know this, well. And the choice Q equals 0, we're going to call type 1. So every time we choose Q equals 0, we call this the type 1 UN theory. Another choice is also of interest to us. That's Q equals -1. This we're going to call the type 2 UN theory. Both of them, we're going to call them at level K. What that means is that the SUN part is level K and the U1 part is determined from that by these formulas. Okay. Now, pure, that's matter-free SUN theories are well known to be level rank dual to type 2 UK Chern-Simons theories at level -n. Okay, so it's level rank duality, but a level rank duality that exchanges an SUN group with a UN group, which is type 2. It's also well known that type 1 UN pure Chern-Simons theories are level rank dual by exchanging level and rank with some signs. But back again to type 1. So type 1 is sort of self-dual, whereas type 2 and SUN are cross-dual. This is well known. I mean, by well known, I mean it's known to the experts in the study of pure Chern-Simons theory. Okay, now the conjectured Bose-Fermi dualities between regular fermions and critical bosons also involve either an SUN duality and a type 2 UN duality on one side, or type 1 and type 1 on the other side. Okay, because these dualities, in the limit that you take the masses of all the matter fields go to infinity, reduce to these well-known pure Chern-Simons dualities. Okay, so as no known duality relates just to SUN theories, we're forced to deal with these slightly irritating UN generalizations, but they're not too bad. You see that? Okay, fine. So these are the theories we're going to be dealing with. Right, these SUN and UN Chern-Simons theories and their Wessel-Witten counterparts. Now, consider a pure Chern-Simons theory on S2 times S1 with M Wilson lines, each at a single point on the S2 and wrapping the S1. Let the Wilson lines be in representations R1, R2 up to Rn, where each of these representations is restricted to be integrable. So over 30 years ago, Witten famously demonstrated that the result of this path integral is an integer which counts the number of Wessel-Witten conformal blocks on S2 with primary insertions in the representations R1, R2 up to R. Now, the number of such blocks can be obtained using the Berlinde formula, but can also be evaluated directly by evaluating a three-dimensional path integral, as was explained almost 30 years ago by Blau and Thompson. We're going to present the answers in this Blau and Thompson language in what follows. So first, I'm going to give you the answer to this question. The answer to the question, what is the path integral when we have these R1, R2 up to Rm insertions in the pure Chern-Simons, pure SUN Chern-Simons theory? The answer turns out to be very simple. What we're supposed to do is this. We're supposed to take all of the representations that we have insertions of and write down their characters. Now, the characters are evaluated on some SUN matrix whose eigenvalues are phases, which I denote by omega1, omega2 up to omega n. Because this is an SUN matrix, the product of these eigenvalues is equal to 1. And, it's a phase, so mod omega is equal to 1. Now, had we been in classical group theory, what we would have done is multiplied these characters with the Haar measure and integrated over the Haar measure in order to get the number of singlets. In order to get the number of what I call Wessel-Witten singlets, or number of conformal blocks, what we do is something very similar. We integrate over the Haar measure, but that integral of the Haar measure is somehow discretized. Instead of summing, we put the same Vandermonde that we would have for the Haar measure. But instead of integrating over all eigenvalues, we're supposed to sum only over discretized eigenvalues. The discretized eigenvalues are those such that the ratios of any two of these eigenvalues are kappath roots of unity. So omega I to the power kappa is equal to omega j to the kappa for all I and j. And of course, all omega I, the product of all omega I is equal to 1. It's easy to convince yourself that the set of all such eigenvalues is finite. In fact, in one-to-one correspondence with the integrable representations of SUN Chern-Simons theory. But we don't need such details. Okay, so you have to do a finite sum over discrete eigenvalues, which is a very particular discretization of the Weil integral formula for singlets of classical group theory to find the number of conformal blocks for SUN theory. Okay, this equation can actually be demonstrated, and we'll show in our paper, that it's equivalent to the Berlinde formula, but written in what I consider much more understandable terms. Okay, that was as far as SUN theory. What about this UN K prime theory. Once again, the UN KK prime theory, the number of Westermino-Witten singlets, the number of conformal blocks, is given by some sort of effective discretization of the Weil integral formula that we would use to compute number of singlets for UN theory. The discretization is over eigenvalues that in this case, of course, continue to be phases, continue to obey the condition that this omega I to the power kappa is equal to omega j to the power kappa, which is that the ratios of these eigenvalues are kappa roots of unity. But in addition, obey another a condition that replaces the rule that product over omega I is equal to 1. There's no reason for product over omega I equals 1 because we're doing UN rather than SUN. But that rule is replaced by this following condition. Product of omega I to the power q times omega m to the power kappa is equal to -1 to the power n plus 1. Now you could ask, for which m is this true? And the answer is it doesn't matter, because from this condition, if it's true for any one m, it's true for every m. Okay, now I've put this factor of -1 to the power n plus 1 in red. The reason I put this in red is that when we generalized the Blau and Thompson integral formula to obtain this result for UN, our at least naive generalization of their method gave us this result without this factor of -1 to the power n plus 1. But we very quickly realized that something was wrong. Then we rewrite this formula by rewriting the Berlinde formula in this form, and we got the same, exactly the same formula, but including this -1 to the power n plus 1. So there's some subtlety here. The path integral gives you phases that at least we were not able to uncover where that came from. So there's a subtle phase in the path integral that naive path integral analysis misses, but the Berlinde formula gets right, and it's very important for what goes on. So this is just to alert you that we're sure that the formula is right because it's the Berlinde formula, but we're not exactly sure how to obtain this right formula from a path integral. Though there's interest, you can also get the same answer from supersymmetric localization. I won't go into this. Okay, fine. So this is the formula for the number of singlets, number of Westermino-Witten singlets, the number of conformal blocks in UN Chern-Simons theory, KK prime theory. Now, in particular, if you choose the particular case Q equals 1, the case I called type 1 theory sometime earlier in this talk, this formula simplifies to this quantity. So this much simpler formula, where, okay, this is the integrand is about as simple as it always was, but this condition here, because Q is 0, this term goes away. So the condition is just that omega m to the power kappa is -1 to the power kappa n plus 1 for all m, which just tells you that every discrete eigenvalue that appears here is either a kappa root of 1 if n is odd, or a kappa root of -1 if n is even. So this is an extremely simple formula. Okay, and it's very easy to convince yourself. Okay, and then as I mentioned, this is a particular discretization of the classical Weil integral formula for UN. And this discretization has a particular property. Because we're summing only over discrete values. And because if you take two of these eigenvalues and put them at the same W, the integrand goes to 0 because of the Wi minus Wj mod square term. Okay? You cannot have more than one eigenvalue per unit 2 pi by kappa in eigenvalue phase space. This tells you that the bound on eigenvalues, the density of eigenvalues that comes out of this formula is bounded. It cannot become too large, cannot become more than 2 pi n divided by kappa. The n is because of the normalization in our definition of the eigenvalue density, and therefore cannot become more than 2 pi by lambda. This may begin to sound familiar. Okay, so in equations, what this says is that if you take the large n limit of this formula, this discretization size becomes 0. So the sum becomes an integral. But this integral is not over unrestrictedly over the whole Haar measure. So it's an integral with the Haar measure, but only over those eigenvalue configurations that obey a particular condition, namely that the eigenvalue density function is less than 2 pi by lambda. Okay, and that is what we call this DUCS. Okay, so it follows that this completely precise finite n formula in the large n limit goes over to this to this quantity. Okay, and from this it's very easy to convince yourself that this IF that I told you about here has a very simple interpretation. It is simply the restriction of the free Fock space to the space, not this time of classical SUN singlets, but of Weston-Witten singlets. The space of invariant number, projected number of conformal blocks. Okay, now that's it for the fermions. I'm now moving on to the bosons. Any questions or comments?
You have 5 minutes, please.
I have 5 minutes. I better hurry. Yes. Okay. Yes. So, okay. So that's where we were for the fermions. Now for the bosons, how does this go? For the bosons, there's an interesting additional twist. You see, this quantity here that that you would get, this twisted partition function over Fock space, okay, can be written as a twisted partition function per single particle state, right? Because that's how any free Fock space partition function is. It always works single particle state by single particle state. For each single particle state, you get a Bose type factor, and these WIs are a consequence of it being twisted. Okay, I've got one for particles here and one for antiparticles. Now, notice that if we take this and we expand it, this expansion runs over all occupations of all these single particle states. They're all symmetrized. And so when you expand it in characters of UN or SUN, you expand it in completely symmetrized characters of UN or SUN with number n boxes in complete symmetrization, where n goes from 0 to infinity. Okay, now the partition function of the bosonic Fock space restricted to Weston-Witten singlets, restricted to Weston-Witten, conformal blocks, is not simply given by this quantity. Why not? This is because it's a famous property demonstrated by Gettner and Witten that any conformal block involving integrable representations and one or more non-integrable representation automatically vanishes. Now, notice that in this expansion here, we have this little n going from 0 to infinity, and when this little n exceeds k, the representation is no longer integrable. So what we're supposed to do, if we want to keep only restrict to the space of conformal blocks of these Weston-Witten singlets, we're supposed to truncate this expansion by hand to n up to, from n to infinity to n up to k. So that's what we're supposed to do here. This truncation to kb is what I've written here. That would be the correct truncation of the free Fock space to Weston-Witten singlets. Now, algebraically, this truncation can be implemented by, allowing it to be non-truncated, and then by killing off the extra terms by multiplying by the appropriate factor. And when you exponentiate, you get what you would have got had you not truncated, plus this extra term. All that's great. But in the large n limit, remember kappa is going to infinity in the large n limit. In the large n limit, it follows that this log here is either 0, that's when y is less than 1, or is kappa times y minus 1. Okay. Kappa times is kappa times log of w. This w is this should be log y. Kappa times log y. Kappa times log y if y is greater than. Okay, that's an obvious property of this thing in the large kappa limit. Okay, and when you plug this in and you do it state by state and you put in all the numbers, you find this precisely reproduces this funny theta function term that we had for the bosons with all the numbers, with all the 2 pi's and v2's. Okay, so both for the bosons and the fermions, all we're doing is taking this free Fock space and truncating to Weston-Witten singlets. So we've learned something important here. Okay, the important thing we learned, well, it's interesting even for the fermions, but I think we've learned something especially important for the bosons. Okay, the important thing we've learned is that in Matter-Chern-Simons theories, no bosonic single particle state, at least at large n, is allowed to be occupied more than k times. Okay, this is a subset of the condition that we're truncating to Westermino-Witten signals, and is what we call the bosonic exclusion principle. Just like fermions cannot be occupied more than nf times, bosons cannot occupy a single particle state more than kb times. Okay, this fact has a very dramatic consequence. Okay, the consequence is this: remember that if you've got a free bosonic theory and you take the chemical potential and you put it above the mass, that theory is ill-defined, because single particle energy states with energies less than the chemical potential become infinitely occupied. Now the bosonic exclusion principle saves you from this catastrophe. The theory is well defined at all values of the chemical potential. Okay, and what you get is some sort of regulated Bose condensate. In fact, under Bose-Fermi duality, this regulated Bose condensate is Bose-Fermi dual to the Fermi sea. Okay, now let me quickly, just in the last 2-3 minutes, let me quickly tell you 1 or 2 other things. I told you about the structure of this partition function for every value of the volume of this S2. This S2, volume of the S2 is large in it's of order n, but there's a parameter for how large in units of n it is. And for every value of that parameter, I've told you about what happens to this partition function. However, it's particularly interesting to see what happens in the limit where this parameter goes to infinity. So we've got this extremely large S2. In this limit, independent of whether n is, though of course these formulas themselves are only valid at large n for the matter Chern states, but for the formulas for the number of singlets, just in the Westermino-Witten formulas for number of singlets, independent of whether n is large or not, it becomes dominated in this limit by a saddle point. Okay, saddle point controlled by the largeness of the volume. And the saddle point tells you that there's only one out of all the summation over this finite number of discrete eigenvalues, only one configuration contributes in the saddle point. And that configuration is a configuration with the eigenvalues being sort of as uniformly distributed around the identity as they can be, consistent with all other constraints they're supposed to satisfy. I've written it out here. Now, as I mentioned up here, the partition function was this product over single particle partition functions, but then summed over all eigenvalues. In the saddle point limit, there's no sum over all eigenvalues, because there's only one eigenvalue configuration that contributes. And so the partition function in some trivial way becomes a product of partition functions over single particle partition functions. And therefore, the full partition function becomes like a product over partition functions, one associated with every state. The explicit partition function per state is given by this formula. It's a deformation of the Bose or the Fermi partition function per state. Okay, and the deformation involves this: that the Bose partition function, for instance, let's say, the Bose partition function per state would have involved summing over these choose factors. It turns out that these choose factors are replaced by Q choose factors, where you use choose factors built out of factorials defined not using by numbers, but Q numbers. Okay. Now, ignoring all the details at the moment, there's a striking fact. In the large volume limit, our partition function becomes a product of single particle partition functions. So you might think that then it must be that in the large volume limit, the Hilbert space becomes a product over Hilbert spaces, one for each single particle Hilbert space. But that we know is not true. We know that's not true because if you look at these single particle partition functions, the expansion is not in terms of integers. It's not got an integer number of states. So something more subtle is happening. The suggestion we make for what more subtle is happening is the following. We propose, and we have some evidence for this, that there is an interesting representation theoretical fact for Westermino-Witten signals. And that fact is this. Suppose I take a very large number of representations of Westermino-Witten theory, sort of randomly chosen, and I fuse them. So I fuse the first two, I get what I get, then I fuse the result with the next guy and I get what I get, and so on. Then I ask, if I go through this process, how many representations in representation N1 do I get? How many in N2 do I get? How many in N3 do I get? And so on. Remember, we only ever get integrable representations, so the set of possible representations is finite. Okay? The answer to that question in general, you cannot know. You cannot know the answer. It depends on the details of which representations you've used. But when the number of representations you've used is very large, even though you cannot know how many representations of each kind you will get, you can know the ratio of the number you would get in representation I and representation J. We claim that this ratio is always given by what is called the ratio of what is called the quantum dimensions of the representation Ri and Rj. I think this is a new and interesting fact about Wessel-Minowitten representation theory. And then once you use this fact, it helps you explain why you get the partition function of your system becomes a product over single particle partition functions, even though the Hilbert space does not. Roughly speaking, the reason is this, that if you've got a single particle state and you want to get an in the end of Wessel-Minowitten singlet, the full representation of everything else in the rest of every other state, apart from your single particle state, has to combine with the conjugate to the representation you're going to keep. And since the number of such conjugate representations, the ratios of numbers of such conjugate representations is independent of what these other states are doing, because of this universality, we get a product of over partition functions. Okay, I'm out of time. I'm sorry I planned this. I should have gone faster. I've already explained to you that we get this universal single particle statistics, the single particle state statistics, that is this interesting deformation of the formulas of either free Bose theory or free Fermi theory. It's a one parameter deformation of the two of these theories. And if you take this one parameter deformation and you turn it into formula for number of particles per occupying a state, you get a deformation of the familiar Bose formula. This deformation is given by this formula. And this deformation has this very nice property that it interpolates in some regimes to the usual Bose formula, but it always cuts off the Bose condensate, and so avoids a boson catastrophe. Okay, I spent all the talk talking about part one, step one. I had some things to say about step two, but very little because it's the uglier part. So let me skip that and go on to the conclusions in future directions. So the conclusions are that we've demonstrated that the partition function of large N Matter-Chern-Simons theories is effectively that of free Fock space constrained to the subspace of Wessel-Minowitten singlets. And then with energies of these states renormalized by forward scattering interactions in a mean field like way. This was step two that I didn't have the time to tell. Okay. It would be interesting to move this understanding away from the large N limit and also from the large volume limit. One target of opportunity here is the superconformal index of Matter-Chern-Simons theories. These formulas for these indices are known exactly, not just at large N. And it would be really fantastic if we could, however, what they mean has never been clear. You have these formulas that are obtained by doing the supersymmetric localization and getting these formulas. But what they mean in terms of what they say about the Hilbert space of the supersymmetric sector has never, at least not to me, ever been clear. And I suspect that there is a version of the statement that we can make at finite n, at least for these supersymmetric quantities, to re-express these known formulas for the superconformal index as an index over some nice Hilbert space involving constraint algebras. I think it would be very nice to understand that. And it would be very nice if the free thermal statistics of this talk showed up in some two-dimensional material. There are many other, that's not out of the question because these theories appear inside the study of the quantum Hall effect. And there are many other things which would be nice to do. Okay, I'll stop here. Sorry for going over time.
Thank you, Shiraz. Thank you for the very nice talk. We have a short time for quick questions, if there are any.
Can I ask?
Hi,
please.
Hi. So can we apply to your technique to some computation of OTOC for?
Yes, I think
OT function,
it should be
possible.
possible. Yeah, I think it should be possible. Now, what? Sorry, let me just clarify, and then you please go ahead.
Right.
What would be relatively easy to do is to compute the OTOC of four charged operators. That is four fermions or four bosons. Now, you may be a little wary about that because here you would be computing a non-gauge invariant correlation function. or more precisely, a gauge invariant coordination function involving some hidden Wilson lines. So not quite the 4-point function of four operators. To compute the OTOC of 4 gauge invariant operators would effectively be computing 8-point functions of the 4 phi's and 4 psi's. Now, 4-point functions, at least in some kinematic limits, we've computed. 8-point functions may be challenging. But okay. Sorry, please go on.
So then, what are you expecting? Is the band saturated?
Oh no, not saturated.
What do you think?
Not saturated at all. You see, these
see.
large N theories are deformations of large N Wilson-Fisher theory. Because in the limit
sorry, pardon, large in what?
Wilson-Fisher theory.
Oh, I see.
Okay. Now, because in the limit k goes to infinity, they become large N Wilson-Fisher theory. Now, large N Wilson-Fisher theory, for many purposes, behaves like a free theory in the strict large N limit. In particular, if you compute the mean free path of two colliding particles, it scales like N. So what we should expect in this theory is that it behaves very far from like gravity, very much like a nearly free theory. This is the reason that these theories are not dual to gravity; they're dual to this weird Vasilian.
I see.
Yeah.
Okay, thanks.
Yeah.
Hi, Shiraz.
Hi, Shai.
So a question about the bosonic exclusion principle.
Oh, hi. Yes,
So
yes.
can these be thought of as some kind of parafermions or parabosons?
Yeah, I would love to understand
of commutation relations which can do this.
Yeah, I would love to understand that in some clear way. Yeah, I would love to. I suspect the answer is yes. Notice though that these are parafermions and parabosons in 2+1 dimensions.
Right,
okay?
right.
So it's not the more familiar thing that people have talked about before, I think. So, but it should be true, but I don't exactly know how to do it, at least not yet.
I see.
Yeah, right.
Okay.
May I ask one last question? As I understood, you start with the matter which is in the fundamental representation.
Yes.
What if we choose matter in different representations of the SUN or UN?
Yeah.
Do you have any results on this?
Yes. Well, we have general results, but no detailed results. So let me say to start with, first thing about matter and the fundamental representation is that these theories become solvable. Now, if you took matter, let's say in the adjoint, the theory is no longer solvable. Let me explain why that's the case. Okay. This is the case because, you see, as you know, we've known for a long time that large N limits with only fundamental matter, fundamental fields are solvable. Typically, large N limits with adjoint type or 2-index matter typically are not solvable. There are exceptions, but that's typically true. Mm-hmm. Now, gauge theories, you might think always fall in the second category because gauge theories always have gauge bosons or the gauge fields, and the gauge fields always have 2-index or adjoint type representations. So typically large N limits of gauge theories are not solvable. However, there's an exception when you deal with Chern-Simons theories because the pure gauge part is by itself solvable using not large N but different techniques, the Witten type techniques. So you say large N matter Chern-Simons theories turn out to be solvable only with basically 1-index matter, like fundamental matter, because there you can sort of marry the solvability of pure Chern-Simons theory and the solvability of matter with just in the large N limit, vector matter in the large N limit. Mm-hmm. Okay, so we don't have any detailed results. However, there are simple general things you can say about the spins of excitations that allow you to ask for what representations could Bose Fermi dualities continue to be true. Mm-hmm. And the answer to that is that there's only a small number of representations for which it could continue to be true. Okay, so you could take, suppose you took, so you take Chern-Simons series with some, let's say some 10-index representation with bosons and ask, could it be dual to fermions? The answer is no. So you can say some general things about these theories using sometimes anomalies or using, well, in our case, more simple things of physical considerations of spins and so on. But the kind of detailed formulas that we have in these theories, we know only how to obtain them only for one index matter.
Okay. Okay. If there are no other questions, let's thank Shiraz again. Thank you, Shiraz.
Thank you. Thank you.
Okay. So we now need to move to the next speaker. Song, are you ready? Please share your slides. Yes. And okay. So
can you see my screen?
Yes, yes. Can you move to full screen mode, please?
Is it okay? Is it okay?
Not okay. Now it is fine. Good.
Okay.
So our next speaker is Song He, and he's going to tell us about the torus partition function and wormhole in TT-bar deformed theories. So the stage is yours, please. I'll give you a warning 5 minutes to the end. Okay.
Okay. Thanks.
Yes.
So first, let me thank the organizer to give me opportunity to talk about my our recent work. So basically, this work based on these two papers, and with my collaborator Sun Yuan, and also Yuxuan Zhang. He is my first PhD student, and also Xianzhou Zhou Xian. He currently stay in Würzburg University in Germany. So I will mainly talk about the torus partition function, and also the second part I will focus on one-dimensional TT-bar deformation. So the outline of this talk, firstly, I will introduce the TT-bar deformation in field theory side, and the second part will mainly focus on the TT-bar flow effect on the partition function, especially focus on the two second-order correction to the partition function in field theory side. And also, we will also talk about the